are going to discuss Taylor series and Lorentz series. So in fact, there is no difference between these two series. Only thing is the negative powers also comes into picture in case of Lorentz series. But in case of Taylor series, only the positive powers are going to be there. That is the only difference. So I hope you people are aware of what is Taylor series, right? So what Taylor series is suppose if there is f of x plus h. So that means h is a minor distance from which is deviated from the x value. And this can be expressed as f of x plus h into f dash of x plus h square by 2 factorial into f double dash of x plus dash 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 up to infinite. Now in the same way, suppose if x being 0, then if the expansion is expanded as if like it is around the origin. So that is, this is the value of x. This is x-axis. Now actually, if you try to find the function value around 0, then this is f of h is equal to f of 0 plus h into f dash of 0 plus h square by 2 factorial into f double dash of 0 plus dash 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 up to infinity. Now, in this kind of cases, what we are going to do is, this h value which is deviated from the origin, which you can treat as x value. Got it? So that's why usually Taylor series is expanded as f of 0 plus x into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus dash dash dash. This is what actually we ideally say this is Maclaurin series. So this Maclaurin series which was derived from the Taylor series. So this is the ideal Taylor series. So this doesn't say about origin. So if there is a function that is defined like this, and then if you randomly consider an x value from there, then a side by point which is at a distance of h, then the function value at x plus h can be found with the help of f of x plus h into f dash of x plus h square by 2 factorial into f double dash of x plus dash 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 up to infinite. So this is under the case of real analysis. Now exactly in the similar manner, we have the Taylor's expansion even in the case of complex analysis also. So do you have an understanding of this Taylor's expansion in case of real analysis? So this I have covered as part of calculus. Got it? Any questions on this? Any questions on this? So now the same thing we are expressing. So this is a real valued function. That means the value of x is only on the real line. But in case of complex series, what happens is a complex number is within a region. So that's why if you randomly consider a region space like this, now this is a point A, let us say. So that point is z is equal to A. Now on this point, if you randomly consider a point called z, then f of z can be expressed as f of A plus z square by 2 factorial z minus A f dash of A plus z minus A whole square by 2 factorial into f double dash of A plus dash 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 up to infinite. This is what we call as Taylor's expansion. Got it? This is the Taylor's expansion. Understood or not? Now this Taylor's expansion, we can prove it. Suppose if you randomly consider a curve, or let us say this is the curve what we are thinking of. Now let us say this distance is at a distance of t, and then this is the point which is located at a distance of z minus a from this. So this distance is t minus a, and this is z minus a. So this line length, what I mean, right? Z minus a. Now let us consider, I'm just proving this Taylor's expansion. Let us consider 1 by t minus z. If you consider this, yeah, so here a is, so in case of complex analysis, whatever the constant or variable you can think of, it is always a complex. So you cannot find even a single real number, right? So even if a is equal to 1, then this is ideally a is equal to 1 plus I0. This is how it is treated. Even if it is a is equal to 1. Ideally it should be treated as a real, but we say this is a complex number by taking 1 plus I0. That's it. Right? So you can think of always the complex constants or the complex variables. That's it. That's why the topic name is complex variables. Now this is, let us consider 1 by t minus z. Now this t minus z can be expressed as 1 by t minus a minus z minus a. So I have added a and I have subtracted a. So this is t minus a minus z minus a. Now here z minus a value is lesser than the t minus a value because the line length, that is from a to t, is more and a to z is less. Now keeping that in mind, if I wanted to make the ratio between t minus a and z minus a less than 1, so that I can found a series which is convergent, then what I can do is t minus a, I will take it out. 1 by t minus a, if I take it out, then this value will be 1 by 1 minus z minus a by t minus a. Got it? Z minus a by t minus a, where z minus a divided by t minus a is less than 1. Now, hence the series is convergent. Is convergent. Now, in this series, if you expand with the help of binomial expansion, because binomial expansion is also a part of Taylor's expansion. All the series, whatever you can think of, the expansions are always a Taylor series. Binomial expansion, then that will be 1 by t minus a, 1 by t minus z is equal to 1 by t minus a into 1 plus or 1 minus z minus a by t minus a whole power minus 1. This you can expand 1 by t minus a into 1 plus z minus a by t minus a (1 by 2 factorial into z minus a by t minus a whole square plus 1 by 3 factorial z minus a by t minus a whole cube plus dash 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 up to infinite. This is the binomial expansion, right? Sorry, I think so. This factorial is not there for the binomial expansion. Yeah. So this is 1 plus x square plus x cube plus dash 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 up to infinite. So this is the binomial expansion for the function 1 minus x whole power minus 1. Now here this value is equal to 1 by t minus z. Now multiply both sides with f of z. With f of t, because this is a function of t. Now if you multiply both sides with f of t, then this side 1 by t minus a getting multiplied by t minus a. This is t minus z. Yeah. 1 by t minus z is equal to f of t divided by t minus a plus z minus a into f of t divided by t minus a whole square plus z minus a whole square into f of t divided by z minus a whole cube plus dash dash up to infinity. So this is the function actually I arrived at. Now if I integrate on either sides, this is a simplified format now. So this is not visible. You first note down this. I am going to write it at the top. Note it down. So this Taylor's expansion, you can write it here. That is, what we have got is f of t by t minus z is equal to f of t divided by z minus a t minus a plus z minus a into f of t divided by t minus a whole square plus z minus a whole square into f of t divided by t minus a whole cube plus dash 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 up to infinity. Now if you integrate on either sides, with respect to t only, we are integrating. So if you integrate on either sides with respect to dt, then this will be, what is the value of this function? What is the value of this integral value? F of t divided by t minus z dt over the closed contour C. So this is the closed contour. This is the closed contour C where we have considered the value of t, and this is any point randomly which was selected within the region of analytic. What is this integral value? No, it's not 0. Solve this already. Somebody tell me, we have solved this already in the previous class. Is it not the way it is integral f of z dz divided by z minus a? What is this integral value? Yeah, 2 pi I times of f of a. This is exactly in the similar manner. This is 2 pi I times of f of z, because instead of z it is a, of t it is z. So that's the only difference. So this is the same integral, 2 pi I times of f of z. Exactly in the similar manner. What is the other values you can think of? What is the first integral? So this is 2 pi I times of, this value will be f of a, then plus z minus a into. So what is this integral value? What is the second integral value? This is 1 plus 1, n plus 1 format, 1 plus 1. So this will be f dash of a, and this is z minus a whole square into f double dash of a plus dash 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 up to infinity. So this 2 pi I will cancel out. Finally, f of z can be expressed as f of a plus z minus a into f dash of a plus z minus a, sorry, there will be 2 factorial here, whole square by 2 factorial into f double dash of a. Similarly, z minus a whole cube divided by 3 factorial into f triple dash of a. This factorial is coming into picture just because of Cauchy's integral formula. What we have used in this entire thing is Cauchy's integral formula. That's it. Got it? So in the Taylor's expansion, it is always Cauchy's integral formula. That's what we are going to use it. So now actually, if there is a region which is analytic, now actually you can state that if a function is analytic, within a circular region, represented by the closed contour, represented by the contour C. Whose center is at A. Then for any random z within the region, f of z can be expressed as you can write this equation. That's it, which is known as Taylor series. Right? So here the condition is the function should be analytic, and this is a closed region, contour region. This is a circular region, and this is the point A. And then within this region, if the function is analytic, a random z value you can express in terms of f of a and z minus a into f dash of a, z minus a whole square by 2 factorial into f double dash of a. This is as if like, if you correlate with the real analysis, this is, if you randomly consider a random value x at this x value for any small change in the value of x to a distance of h, then f of x plus h, or the point while, so instead of h, it is z here. Instead of x, it is a here. So we are representing a and h, z values here because this is a region. This is a two-dimensional representation. This is a single dimension, right? So the x value is only one dimensional. So that's why x plus h can be expressed in terms of f of x. Exactly in the similar manner. So that is a plus z, or the z value can be expressed in terms of f of a. That's it. Got it? So that is the correlation between the real analysis and complex analysis. The only difference is this is a complex number. This is a real number. So real number is always a single line, and complex number is always a region. So that's the reason here region is covered within a circular region. Right? So because why we are identifying this as a circular region is because we are expressing this Taylor's expansion within a small change in the value of x, that is x to x plus h, where h tending to 0. Now here also, this is a small region of circle. Got it? Where in and around of A, we are trying to express the Taylor's expansion. Got it or not? You can note down this. So for this, you can express f of x plus h is equal to f of x plus h into f dash of x plus h square by 2 factorial into f double dash of x plus dash dash dash. That is real expansion. This is complex expansion. Last line. This is, I'll just read it. If a function is analytic within the circular region represented by the contour C, whose center is at A, whose center is at A, for any random z within the region f of z can be expressed as f of z is equal to f of a plus z minus a into f dash of a plus z minus a whole square by 2 factorial into f double dash of a plus z minus a whole cube divided by 3 factorial into f triple dash of a plus dash dash dash, which is known as Taylor's expansion. Got it? So this is about the Taylor's expansion. But usually this is just a derivation saying that you can express f of z in terms of f of a. But you don't need to use this derivation at all. You will be straight away using the binomial expansion, which is again derived from the Taylor's expansion only. So binomial expansion is the base to expand any function which is in the complex domain. Got it? So we don't be using it. So but I am just proving this can be expressed in this format. That's the only thing. Clear or not? Any questions on this? So note it down. Okay. Now Laurent series. You don't need the proof for Laurent series, but the proof also exactly lies in the similar manner. But only difference is Laurent series comes into picture if the region is not circular. Rather than circular, it is a ring-shaped region. If it is a ring-shaped region, then there are two different boundaries for the ring. So that is, if there is a closed contour or closed circle like this, and there is one more closed circle like this, then within this ring-shaped region, let us say this radius is R1 and this radius is R. Then R is greater than R1. Now this is the region of integration. Now within this region, if the function is analytic, then for any random z which is located within this region, this is the z. Now this is A. Exactly in the similar manner earlier, right? So there will be one circle whose center is A and the region of the circle is analytic. Now in this case, the region of circle is bounded between two different shapes. So this is one circle and this is another circle. The function is analytic within this region. In such cases, there are two different circles. So this is one circle whose radius is R and this is one circle whose radius is R1. Now if you randomly consider a z here, earlier actually we have considered the t value at this point. Now if you consider the t value at this point and then here, so z minus a by t minus a is less than 1, provided if you consider the t value on the top boundary. Suppose if you consider the t value on the bottom boundary, then this value comes into picture, that is t minus a divided by z minus a is less than 1. This is the difference. So that's the reason in the Laurent series expansion, if it is bounded between two different ring shapes, then the Laurent series f of z for any random z which is within the analytic region, it can be expressed as sigma n is equal to minus infinity to plus infinity an into z minus a whole power n into an. Got it? So where an actually we found with the help of this an is 2 pi I times of so this is a random curve which you can think of in between any closed contour or any boundary also you can see. So this curve usually it is represented with a curve name called tau. So if you randomly consider a closed contour within that region, that integral value 2 pi I by n factorial into over the contour tau f of t by t minus a into dt is nothing but a. So here the expansion is from minus infinity to plus infinity, which essentially means that here a naught plus z minus a into a1 plus z minus a whole square into a2 plus dash 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 up to infinity, and then from the negative side also a minus 1 z minus a whole power minus 1 plus a minus 2 z minus a whole power minus 2 like this actually. On the negative side also it will be expanded. I'll just write it here. Z minus A whole power minus 3 into A minus 3 plus A minus 2 Z minus A whole power minus 2 plus A minus 1 Z minus A whole power minus 1 plus A naught plus Z minus A into A1 plus Z minus A whole square into A2 plus dash 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 up to infinity, and this side also up to minus infinity. This is the Lorentz series expansion. Got it? You don't need the proof for it, but the proof exactly lies in the similar manner the way we have done it. So only difference is two different curves you are going to take it up. One is C1 and another is C. Now in C1, so if inside is the C1, in C1 T minus A by Z minus A is less than 1. You have to expand this one. And C2 or the outer contour, this is Z minus A by T minus A is less than 1. Now you have to expand the binomial expansion with respect to this. Got it? So this is the Lorentz series expansion. So the properties of Lorentz series are, one is it should be expanded. So Lorentz series, we will get this if the function is analytic within a ring shaped region. A ring shaped region. This is first thing. And a Lorentz series will contain, negative powers of Z minus A. So this is one key factor. So these are the two important properties of Lorentz series. So Taylor series and Lorentz series, there is no difference. Only thing is, Taylor series you are going to get it if the region is circular and it is analytic within that circle. You are not going to get any negative powers of Z minus A. That is Taylor series. In Lorentz series, you are going to arrive at a negative powers, which we call as the Lorentz series, provided if the region of analytic is within a ring shape. And you are going to get the negative powers of Z. That is the difference. Clear? Do you have any questions on this? Any questions on this? T minus A by Z minus A. Now if you consider T on this line, right, then Z minus A by T minus A is less than 1. If you consider T on this line, then T minus A by Z minus A. T minus A is this length and Z minus A is this length. So T minus A by Z minus A is less than 1. So if you understand the Taylor series clearly, there I have used one important property for the expansion with the help of binomial expansion for a convergent series, wherein I have identified a contour. So this is the closed contour. Within this closed contour, this is a random Z. Now you have considered the T value on this, then this is the point A. Then I have expanded this Z minus A by T minus A, being it is less than 1. I have expanded this as a convergent series of binomial expansion. The same property, we are going to use it even in the Lorentz series in this format. You have to assure this condition less than 1. Any questions on this? So this is about the Taylor series and Lorentz series. Now we are going to solve some problems on this. And one important property of this is Z minus A whole power minus 1 into A minus 1 plus Z minus A whole power minus 2 into A minus 2. Here this A minus 1, it plays very critical role. This is what we name as residue. Residue. So there is something called residue theorem, which we are going to take it up in the upcoming class. So this residue theorem says that if the function is not analytic at one point where at z is equal to a, if the point is singular or if the function is not analytic at that point, then the residue value at that point, which is nothing but the coefficient of z minus a whole power minus 1 times 2 pi I, is directly the integral value. That's what the residue theorem says. Got it? Okay. So here you remember that the coefficient of z minus a whole power minus 1 is critical. So in the residue theorem, which we are going to use that. Expand f of z is equal to 1 by z minus 1 into z minus 2. Z minus 1 into z minus 2 in the region case 1 mod z less than 1, case 2 1 less than mod z less than 2, case 3 mod z greater than 2, case 4 0 less than z minus 1 less than 1. Now, in all the 4 cases, try to expand this function. So here we will be, so you may get either Taylor series or Laurent series depending upon the situation. Here, what is the kind of series you are going to get in case 1? The Taylor series or Laurent series? Will be Taylor series. Case 2. So case 2 is Laurent series. What about case 3? Three and 4 both. Taylor's and Laurent. I don't think so. This will also be Laurent series. Let us see what kind of series we are going to get it. So this is the Taylor series and all other 3 are the Laurent series. Now let us see how we are going to get it. Now this value f of z can be expressed as the partial fractions if you wanted to identify. How can I write that? So this can be written as z minus 1 minus z minus 2 divided by z minus 1 into z minus 2. This you are going to get as 1 by z minus 2 minus 1 by z minus 1. This is the expansion. Now, so there will be a shortcut for these values. To identify this value and this value, there is a shortcut for it. So here, if you wanted to identify, suppose this f of z can be expressed as a by z minus 1 plus b by z minus 2. This is how if you want to expand it. Then if you want to find out the value of a, what you can do in the original function is try to make the value being 0. So this actually you make it 0. If I make z is equal to 1, this part will be 0. For that, I make just z is equal to 1 and I will close this. Then 1 minus 2, 1 by 1 minus 2 is nothing but minus 1. So this a will be minus 1. Similarly, if you want to find out the value of b, then for what value of z you are going to get 0 at the denominator, that is z is equal to 2. Then try to keep z is equal to 2 and close that value. So 2 minus 1 is plus 1. So this value will be plus 1. So this is a shortcut to identify. Got it? Understood or not? Yeah. So once you get these values, then you can expand it. So this I will write as 1 by z minus 2 minus 1 by z minus 1. Now here the condition is mod z less than 1. So here this can be written as 1 by z minus 2 plus 1 by 1 minus z. Mod z less than 1, this is the condition. If mod z less than 1, here also what I will do is z minus 2, right? So I will take 2 out. So that is 1 by 2 into z by 2 minus 1. Or minus also you can bring it out. This is plus and minus. So this function you can write it as 1 by 1 minus z minus 1 by 2 into 1 minus z by 2. This is how I can write it. Because if mod z is less than 1, mod z by 2 also is less than 1. This is how you can arrive it. Is this understood? I hope you understood why I have written in this format. I have taken 2 out and then I have written as 1 by 1 minus z by 2. Why I have written this way? Rather I should have kept as 2 minus 1, right? 2 minus z. See this. Here what I have written is, first actually I did the partial fractions and then I got this value. Then I have simplified that format as, I have written 1 by z minus 2 plus 1 by 1 minus z. So here 1 minus z, why I have written as, so this is minus and this I have made minus and this plus. That is how I have written there. Multiplied with minus 1 top and bottom. So I am going to get 1 by 1 minus z. So because actually usually for the binomial expansion 1 by 1 minus x, this is how you will treat. You don't usually keep as 1 by x minus 1, though it is correct. You don't keep it that way. You will multiply with minus and bring this to the other side. That is more convenient for the binomial expansion. That's what I have done. Got it? Now here I got this value. This is fine perfectly. Because the region of convergence is mod z less than 1. So he has given the circle region. Mod z less than 1 is nothing but a circular region like this. And this radius is 1. Then the second part is 1 by z minus 2. 1 by z minus 2, if I write it in the standard format of 1 by 1 minus x format, then this is 1 by 2 minus z. So 1 by 2 minus z, I will write as, so minus of 1 by 2 minus z, I will just write it here. Minus of 1 by 2 minus z. Now 1 by 2 minus z, I have written in the format of 1 by 1 minus z, then minus 1 by 2 into 1 minus z by 2. This is how I have written. I have taken 2 outside. Why I have written 2 outside is, the simple reason is, I wanted to expand as a convergent series. Now, for the standard binomial expansion, that is 1 plus something. 1 plus something, but it is 2 minus something. So, if I bring 2 outside, then I will get 1 minus z by 2. Now, actually I can compare with the binomial expansion. But for a convergent series, I have to assure one more condition, that x value should be less than 1. For that, I will be using the standard condition whatever he has given, mod z less than 1. If mod z is less than 1, mod z by 2 is also less than 1. Got it? So, suppose if I consider here, this is mod z by 2, this radius is 1 by 2 only. So, it is anyway less than 1. Got it? Then you can expand with the help of binomial expansion. 1 plus z square plus z cube plus dash 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 up to infinity for the first expansion, minus for the second expansion 1 by 2 times of 1 plus z by 2 plus z square by 4 plus z cube by 8 plus dash 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 up to infinity. Now this needs to be simplified. That's it. So is it a Taylor series or Laurent series? Is it a Taylor series or Laurent series? Somebody tell me what is it? Samrin, it's not Taylor series. Did you notice any negative powers of z in this? There is a negative powers of z, then only we say it's a Laurent series. There are no negative powers of z. So this is again a Taylor series. You need to simplify it. 1 minus 1 by 2 is plus 1 by 2 and z plus z by 2 is 3 by 2 times of z, and then z square plus 1 by 4 z square. So this is 5 by 4 z square. So if you expand this, so after simplification, this is 1 by 2 and then z plus z by 2 minus z by 4. Sorry, 1 minus 1 by 4, that is 3 by 4 times z, then z square and then minus 1 by 8. So this is plus 7 by 8 times of z square plus 15 by 16 times of z cube plus dash 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 up to infinity. If you notice, there are no negative powers of z in it. So that's why this is a Taylor series. Here, you are not going to get a Lorentz series because the region of convergence is mod z less than 1, which is a circular region. Exactly in the similar manner, you try to solve the second one. If mod z less than, so 1 less than, mod z less than 2. So exactly in the similar manner, try to expand. To try to expand the same function. Let us see what you are going to get it. Yeah, it will be a Lorentz series. Okay, so let me solve this. See this, exactly in the similar manner what we have done in the previous case. So this expansion can be written as, so the same thing, 1 by z minus 2 minus 1 by z minus 1. So this is the function. Now here the condition is 1 less than mod z less than 2. Now this can be divided into two parts. One less than mod z and another case is mod z less than 2. These are the two cases. Here mod z by 2 is again less than 1, which you can derive from this. But in this case, here 1 by mod z is less than 1 or 1 by z mod is less than 1. So this is one case and this is another case. So these are the two regions, right? So it will be a ring shaped region. Hence, two conditions we are going to get it. Now these two conditions we are making use of here. See this. Now here, first case, z by 2 is less than 1 and another case is 1 by z is less than 1. So here, mandatorily what I need to do is 1 by z minus 2 minus 1 by z if I have to take it out, and then this I will write as 1 minus 1 by z. So why I have written as 1 minus 1 by z is this part what I have got, right, it should be less than 1. That is the condition. So that I can make use of binomial expansion. So keeping that in mind, I have taken z out. And for this case, the condition what I have got is mod z by 2 is less than 1. So here I will take 2 out. That is 1 by 2 times of minus also I will take it out. 1 minus z by 2. So minus 1 by z into 1 minus 1 by z. These are the two cases. So this is minus 1 by 2 and then in the numerator I can write as 1 minus z by 2 whole power minus 1 minus 1 by z into 1 minus 1 by z whole power minus 1. So this you need to expand with the help of binomial expansion. This is minus 1 by 2 is out and then 1 plus x square plus x cube plus x power 4 plus dash 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 up to infinity. This is minus 1 by z and then this expansion is 1 plus x plus 1 by x square 1 by z cube plus 1 by z power 4 plus dash 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 up to infinity. Now if you notice here, you can simplify it. Here if you notice, the positive powers of z are present here, and here if you notice, the negative powers of z are present here. Hence it's a Lorentz series. This series you can simplify it after additions, subtractions and then multiplications with these constants. If you do it, you are going to get a series of the form integral minus infinity to plus infinity an into z power n. So this is a Lorentz series where this is varying from minus infinity to plus infinity. That's what you have got. Got it? So did you notice how we have got the Lorentz series? But only understanding is here you need to appropriately bring the conditions so that the x value or the other part of the binomial expansion should be always less than 1. This is the only thumb rule. Got it? Note down this. This is a Lorentz series. So the same expansion, but depending upon the region where you wanted to expand, right? So you may get either a Taylor series or a Lorentz series, depending upon the region. So same function, but different regions. That's it. Note it down. Then yeah, so you try to solve and then try to expand it. Here the condition is mod z greater than 2. So if mod z greater than 2, then 1 greater than 2 by z. So this is the condition. Or 2 by z mod is less than 1. This is the condition which you wanted to expand for. If 1 by z, if 2 by z is less than 1, definitely 1 by z is also will be less than 1. This is the condition which you are going to use it. Got it? Okay. So try to expand for case 3. So try to solve 4 also. Now actually, okay. So I am assuming that everybody is done with case 3 also. Let me know if you are not able to solve it. Anybody wanted me to solve case 3? Now in case 4, this is condition is given as mod z minus 1 is less than 1. So how this forms a ring shaped region, right? Why it forms a ring shaped region is mod z less, so mod z is greater than 2. So this is the lower boundary, mod z is greater than 2. Right? So this is the lower boundary. Now the region of integration is outside this. Now the other ring radius is infinite. Got it? Karandeep? So now actually this case mod z minus 1 is given. In such cases, what you have got the information is only mod z minus 1. Now in that case, what you have to do is, so the region has to be expanded only in terms of z minus 1 only, because the region what he has specified is, this is x-axis and this is y-axis, then z is equal to 1 is this point. Now from here there is a radius, so this is a ring here, not at 0, 0, the way we have done earlier. Now this is at z is equal to a, this is a most generic case, so z is equal to 1. Or z minus 1 is equal to 0. So that is the center of the circle where you wanted to find out the Taylor's expansion. Here, if mod z minus 1 is less than 1, then you can expand in terms of z minus 1. This is 1 by z minus 1 into z minus 2 can be written as z minus 1 minus 1, or minus, if you take it out, minus 1 by z minus 1 into 1 by 1 minus z minus 1. So here I will keep this as it is, minus 1 by z minus 1, and then this I will write as 1 plus 1 minus z minus 1 whole power minus 1. This is minus 1 by z minus 1 into 1 plus z minus 1 plus z minus 1 whole square plus z minus 1 whole cube plus dash 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 up to infinity. Now this is minus 1 by z minus 1 and then minus 1 minus z minus 1 minus z minus 1 whole square minus dash 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 up to infinity. So this is the expansion. Now is it a Taylor series or Lorentz series? It is a Lorentz series. Yeah. So do you have any questions on this? So this is how you will be expanding with the help of Taylor's expansion or Lorentz expansion. Sometimes actually the problem statement is asked expand about a point. About a point means suppose expand about z is equal to a. This is how he is going to point it out. Expand about z is equal to a, which essentially means that he asked us to expand in terms of z minus a. That is another way of asking the same problem. Because in UPSC, that is how actually he will be asking. So expand about z is equal to a. That means you will be expanding with the help of z minus a terms. So the way we have done in this case, z minus 1. Expand about z is equal to 1. That is the other way of asking the same problem. Right? So this is about the Taylor series and Lorentz series. I am going to give an assignment on this. So in the next class, I am going to explain the residue theorem. So residue theorem, so this coefficient of z power minus 1, so z minus 1 whole power minus 1 is there, right? So this is the coefficient, here it is minus 1. This is what we name as residue, so which we are going to use the residue theorem. So in the residue theorem, the integral value you will be able to find out without even finding out the integral value, just by looking at the residue, multiply with the 2 pi I, that will be the direct value of the integral. Got it? So that is another way of finding the integral, the way we have done in case of Cauchy's theorem, where without even identifying the integral value, you are straight away saying that if the function is region, so if the function is analytic within the region, the value of the integral will be 0 itself. Suppose if the function is failed to have an integral, failed to have a analytic point at one point, then there actually you will be identifying, right, a small circle and then try to use with the help of Cauchy's integral formula and then identify the value as 2 pi I times of f of a. Exactly in the similar manner, that f of a value, we will prove that that will be equal to the a minus 1 coefficient in case of Lorentz expansion, right? So that's what we use as residue theorem. Same thing, whatever the value we found as f of a there, that will be equal to a minus 1. So instead of that, we will state as this as the residue theorem, because you are using the residue value, which is nothing but a minus 1. Clear? So there is a significance for z minus 1. Why? Because this z minus 1 is less than 1. This is the condition what we are going to use. That's why z minus 2 I have written as z minus 1 minus 1. That is how I have written. Why I have written that format is, I need to expand about z minus 1. And there I need to expand, so there I need to assure z minus 1 value is less than 1. And every term will be coming as z minus 1, keeping this in mind. Got it, Hitesh? In the last part, there is only one part. No. So this is it. So this actually I didn't even touch to expand. This part only I expanded because he asked us to expand about z minus 1. So if it is z minus 1, which is already there, then what I need to do it for it? So there is nothing can be done on this. So only part is z minus 2, which I need to expand in terms of z minus 1. That's why I have separated in this format and tried expanding with the help of binomial expansion. This I kept it as it is without even doing the partial fractions. Clear, Kirandeep? In the final solution, this is, I have multiplied this, right? So minus 1 by z minus 1, and then there is minus 1 term because z minus 1 and z minus 1 will be cancelled out. This is a minus 1. This is, so this expansion is a minus 1 into 1 by z minus 1 plus a naught plus a1 into z minus 1. This is how we got this. So this is a Lorentz series, but the Lorentz series ended at this point, and there are no higher negative powers of z minus 1. Got it? Yeah, so in third case, we will not touch z minus 1 because, so the condition what he has given is, he asked us to expand about z minus 1 itself, which is already there. So there is no need to touch this. You are not even doing the partial fractions also. Got it? So in third case, okay. So in third case actually, you will be expanding in terms of z. So there actually, so this actually we have done, right? So I think so mod z greater than 2, that means 2 by z is less than 1. Then you have to touch z minus 1 and you have to touch z minus 2 also. Let me explain that and close it. So in the partial fractions, 1 by z minus 2 minus 1 by z minus 1. And the condition what we have got here is mod z greater than 1 or 2 by z is less than 1. Right? 2 by z is less than 1. Now here, if 2 by z is less than 1, 1 by z is also less than 1. Obvious, right? So here, 2 by z is nothing but if I take z out from this, 1 minus 2 by z. And then minus here, 1 by z into 1 minus 1 by z. 1 by z into 1 minus 2 by z whole power minus 1 minus 1 by z into 1 minus 1 by z whole power minus 1. So this is the expansion which you need to expand it. Got it, Samrin? Understood or not, Samrin? Okay. So this is straight away binomial expansion. That's it. Yeah. So that's all for today. So upcoming class actually I'm going to discuss the residue theorem. So I'm going to give an assignment on this. Yeah. Thank you. Yeah. Good night.